Hi there, Algebra 1. Today we're doing 4.3 patterns and nonlinear functions. Objective: to identify and represent patterns that describe nonlinear functions. Linear and nonlinear function. A linear function. A linear function is a function whose graph is non-vertical line or pattern of a non-vertical line. So we have right here, this is a vertical line. This would be a vertical line. This is a vertical line, or a linear line. I shouldn't say vertical. Linear. Okay, non-linears are going to be what we have here, which is a parabola. I can't remember what these are called right off the top of my head. And this is going to be absolute values type of line. So, nonlinear functions are, nonlinear function is a function that is a function whose graph is not a line or a pair of, or part of a line. Okay? Classifying functions as linear or nonlinear. The area A in square inches of a pizza is a function of its radius r in inches. The cost in dollars of the sauce for a pizza is a function of weight in ounces of sauce used. Graph these functions shown by the table. Is each function linear or nonlinear? Okay. So on this one, I'm going to make a pretty big size graph. Okay. Radius is going to be over here, and we're going to have area over here. Area. I'm going to go up by, I don't even know if I want to go up by tens. Maybe let's go 20s. 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 240, 260, 280, 300, 320. Alright, so the first one is with a radius of 2, so 1, 2, and that's going to be about 12, so we're going to be somewhere about there. Now we're going to go 4. Okay, my radius is 4, and we're going to be about 50, so we're going to be somewhere around here. Obviously, probably don't know if this is linear or not yet, because we only have 2 points, and we can make a line through 2 points. Alright, 6. Six is 113. Okay. 8 is 201. Okay, and then 10 is 314. So, do you think that's linear? I would probably say no, because to me it looks like it's going to be like a half of a U. Okay? So that one, I would probably personally say is not a function. I can't say not a function. Graph each function shown in the table. Is the function linear or nonlinear? That's what we're looking for. I would say it's nonlinear in this case, because of the fact that it is not a straight line. Okay, now we have the other one. Now my big graph could probably be erased because now. Okay? So, we want to know if this one's linear. So we're going to have weight. I'm going to put weight down here. And cost. Alright. 1, 2, 3, 4. That one's kind of close. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's what I need. Okay, we're going to go by ones. 1, 2, 3, 4, 5. And I need to get that out. Alright. So, at 2 pounds, it is like 80 cents. So, probably about right here. Alright, now, at 4 pounds, it is $1.60, so right in there, what's that? 6 pounds, it is $2.40. Okay. 8 pounds, it is $3.20. At 10 pounds, it is $4. Okay, this one is not completely linear as I did it on my graph, but I'm just going to guess based off the fact that it is pretty close. I'm guessing my graph is just skewed a little bit, and this one would be a linear function. Okay, the table below shows a fraction A of the original area of a piece of paper that remains after the paper has been cut into halves and times. Graph the function represented by the table. Is the function linear or non-linear? Well, okay, so cut numbers, I'm going to put that on the bottom. So cuts, and I'm going to put remaining. Alright, so we have something like this. More than likely, the way this looks to me, we're probably going to go in a negative direction. Alright, so we got 1 cut, we have 2 cuts, we have 3 cuts, and we have 4 cuts, right? We start out here with, let's say, we're going to skew this a little bit so it's easier to see. We're going to start out with, after 1 cut, you have a half. So we're going to say this is 1/2 here. Alright? Probably started out with a whole piece. Alright? 2 is going to give you a 1/4. So that's going to be about half the distance here. This is 1/4. This is going to be another half. That'll be 1/8. And then we're going to get 1/16, which is half here. Okay? Then it wants to know if this is linear. Well, right now I would say not, because of just my drawing. It's starting to level out like this, and it will start going like this on and on forever, and slowly get closer to this line. So, I would not say this one's linear. I would say this is non-linear. Would be my answer to this one. The table shows the total number of blocks in each figure as a function of the number of blocks on the edge. What is the pattern you see to complete the table? Represent the relationship using a word, an equation, and a graph. Oh, we're going to love these questions. Alright. So, first off, The table show, okay, so what is the pattern you can use to complete this? Well, if you see, basically what I'm saying is every time we are cubing the number of blocks on the edge, we are cubing that. Okay? Is what I am seeing. So, okay, so that's what I'm seeing. So, on 4 here, 4 cubed would be 4 times 4 is 16, times another 4 is 64. So that would be 464. 5 would be 5 times 5, which is 25, times another 25, which is 125. So that would be 5 and 125. So I completed the chart. Now, it says, go kind of back to yesterday's lesson of using words and equations. So, my equation, once again, that is the thing that I prefer to do first. It just seems easier to me. Okay, so my equation I already talked about, what I thought was happening. So, we are basically taking what they are calling their x's, which is the blocks on the edge, so that's my x. They're cubing it to get my output, which is total number of blocks. So that would be my equation. So, now you have to turn that into words. Well, Mr. Riedel, yesterday we never talked about cube. So, in this case, to find it, you would take the blocks on the edge cubed to get the total number of blocks. Okay. So, number on the edge here is 1, right? 1 cubed is 1. Number of blocks here is 4. Or is 2 on the edge. Alright. So there's only 2. Okay? We cube that, we get 8. Well, there'd be 1, 2, 3, 4, 5, 6, 7, 8. Work. Alright. Number of cubes on this, on the edge, is 3. 1, 2, 3. Alright. You're going to get another 3, so there's 9 there. 18, 27. It works. Okay? Now graph this. And this is not going to be another fun one to graph. So, okay. So at 1, it was 1. So you probably got something like down on the edge right here. Alright, 2 was going to be 8. Well, that's going to be not quite there. 3 was going to be 27. Okay, 4 was going to be 64. 5 is 1. 125. I did it wrong. You have something like that. That is obviously not a linear function. So that one is nonlinear. Okay, the table shows us the number of new branches in each figure of the pattern below. What is the pattern you can use to complete the table? Represent using words and an equation. Oh joy. Alright, so what is the pattern? Well, I would say we're doing cubed again. No, we're multiplying by. Interesting. Okay, we go to 1, 3, we go to 2. I think what's taking place here, maybe I'm wrong, but I think that's your exponent. It's going to be 3 to the x. And that is my assumption. Okay? That is kind of what I'm getting out of it anyway. Okay, so we get 4, so we're going to get 3 to the x power, and that's going to be my y. Alright, to finish my pattern over here, 3 to the 4th, well that's going to be 3 times 3, which is 9, times another 3 is 27, times another 3, must be about 81. Okay, take that by another 3, must be like 243. I'm not 100% sure off the top of my head. But that's what I'm thinking it is anyway. Okay, and of course, I was correct on that one. Alright, so now we need to put it in words. I've created my equation. I like my equation. I don't know. It might be because I'm a math teacher, whatever. But I think equations make life easy. Okay, so now we are going to put it in words. Well, to find the number of branches, we take 3 to the x power, and that gets us the total number of branches. Okay, we go here. So we're at this point. That line is not straight. It is but closer. Okay. Number of figures. And I went up by 50s. Partly because it'll be a lot easier. So 1 to 3 would be really far down here, probably farther down than I got it. 2, that would be maybe a little bit higher. That's probably too high anyway. 3 would be to the 27th. That should be about halfway through here. 4 is to the 81st. So that should be here. And 5 should be up here. So you have something going like this, in which case it will take off dramatically. Okay. Write a rule and describe a nonlinear function. The order pair 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32 represent a function. What is the rule that represents this function? Okay. Okay, so let's make a chart real quick. Just out of curiosity. To see what it looks like. Alright, so we have X, Y. Okay, we have 1, 2, we have 2, 4, we have 3, 8, we have 4, 16, and we have 5, 32. Okay. So we could multiply by 2, that works here. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. Oh, that made us mess up. So that's not it. So that kind of throws a lot of things out that we can't do. We have x plus 1. Well, that works for the first one, but that's about it. I don't know. In our last problem, we were squaring it by the x value. So let's try that, just out of curiosity. So we have 2 to the first, that would work. That gets me 2. 2 to the second gets me 4. 2 to the third should give me 8. Oh, that looks like it's working. 2 to the fourth equals 16. 2 to the fifth equals 32. I would say our rule is going to be 2 to the x power. If I was going to take a guess. So y is going to equal, I didn't finish my rule, I guess. Y equals 2 to the x power. Some of these you're going to have to try. Some of them you see. I personally knew the answer from that one, but I know you're not going to see it that easily. There is your homework.